Welcome to Part 4, Equations and Graphs of Trigonometric Functions. In Section 1 of Chapter 4 of the unit Circle, trigonometric equations were solved algebraically. You can also do this graphically. Practical applications of trigonometry can be represented graphically, such as phases of the moon, motion of a child on a swing, or a Ferris wheel. Alright, so two methods to solve graphically are: you can either graph each side of the equation separately and find where the graphs intersect, or you can rearrange the equation to get all terms on one side and then graph and find the x-intercepts. I've got a couple of examples. The first example I will do using the first method and the second example using the second method. Okay, as you can see, I've already pre-scaled the graph. So again, if you want to pause the video to do your own scale to match mine, go ahead. If not, then follow along with what I'm doing now. Okay. So, if we're solving the first one graphically, I'm going to put the left side on, and I'm going to put the right side on, and then we're going to see where and if they intersect. Okay, so 4 sine theta minus 5. We have a vertical stretch by a factor of 4, so that means our amplitude is now 4 instead of 1, and a vertical translation of 5 units down. So that means it will start here, and it will hit its maximum here, because the amplitude is 4, so up 4. Okay, and it will come back down to cross the median at 180, and we'll actually go down here below to our minimum, and then back up to the median at 360. Okay, so there's the graph of 4 sine theta minus 5. Okay, so the other side, the right side of the graph, says that we are x equals 3, or y equals 3. So we're going to draw a line through y equals 3. So to find the solution, we see where the two graphs intersect. Well, if you'll notice in this case, they don't intersect, so therefore there is no solution. Okay, that was easy. All right, next one. This graph is yucky. I strongly recommend that you take out your calculator and put it in radian mode, because again, we're between 0 and 4 pi, and type that in and make a nice sketch on your screen here. You'll see that the asymptotes are all at pi over 2's, so I'm going to just draw those in. Okay, so 1 pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. Okay, so there's all our asymptotes. All right, and it crosses the x-axis at 0, pi, 2 pi, and 3 pi. Okay, and it also crosses the x-axis on its way back up just before the asymptotes. So right here, and right there, and right there, and right there. Okay, so it's kind of a weird looking graph. It goes down like this and then up. Sorry, all your asymptotes should have arrows on the ends of them. Again, it's a tangent graph, so there's no surprise here that this has asymptotes. Okay, and then this kind of comes like that, and down and up, pretty much straight. And again here on the same side, because of course the repetitive nature of the trig functions, all of these sections are going to look an awful lot alike. Alright, good. So, if you'll notice then, we have 8 x-intercepts, and they are at, so theta equals 0, pi, 2 pi, 3 pi, and then you want to use your graphing calculator to find your zeros, which are also at 1.25, 4.39, 7.53, and 10.7. Approximate values, not exact. Okay, great. Number 2. Write a sinusoidal equation that models the average temperature in Brandon, Manitoba, as given on the table. Okay, so if you'll notice, we start at a minimum. So we're going to use a cosine, in this case, as our formula. So y equals a cos b of x minus c plus d. So let's figure out what all of our values are. A is the amplitude, so that would be max minus min divided by 2. So my maximum temperature is 18.9. Take away negative 18.3 divided by 2 gives us 18.6. Our D value is max plus min divided by 2. So that's 18.9 plus negative 18.3 divided by 2, which gives us 0.3. Okay? The period, whenever we are doing problem solving with trig functions, we'll always use 2pi instead of 360 degrees. Most of the applications work better with that. Okay, so period is 2pi over b, which means that b is equal to 2pi over the period, and the period is 12 days, or 12 months, sorry, so 2pi over 12, which is equal to pi over 6. Okay, and because we are using cosine, we don't have to worry about a horizontal shift. We just have to make sure we do a vertical rotation, because we're starting with the minimum on the x-axis, on the y-axis, sorry, instead of the maximum. All right, so let's fill in what we know. A is 18.6 cos of b, which is pi over 6, times x, because there's no horizontal shift. And again, don't forget to make your first value negative because we reflected over the x-axis. Okay. And then plus 0.3 was our median. Okay. Now, this does shift it a little bit because January is the first month, but we actually put it at as the 0 month. Okay. So if you wanted to shift it so that January is the first, then you can shift it horizontally by, instead of having this as being pi over 6 times x, you can make it pi over 6 times x minus 1, and that would shift it back so that January is indeed the first month. Okay? All right, let's try the next page. Example question number 3. Excuse me. Okay, so the London Eye has a diameter of 122 meters, and it's 135 meters from the ground to the top. It takes 30 minutes for one rotation of the wheel. Passengers board at the bottom of the ride, and the wheel moves slowly enough that it is not necessary to stop to let passengers on or off. Write a sinusoidal function that represents the height of the passenger riding the London Eye. Over what domain is the function valid? Okay, so we're going to use sine in this case. And again, same thing as last question. We need to figure out what A and D and B and C are. Okay, so A, of course, is our amplitude. Now, when you're given questions with circles, remember that on our unit circle, the amplitude of a sine and cosine function was 1. That corresponds to the radius of the unit circle. So the same will be true here. If the diameter is 122, then amplitude will be the radius of that circle, which is 122 divided by 2, or 61 meters. Okay? Now, it's 135 meters from the ground to the top. So, how far above the ground does that make it then? Okay. Well, we have 135 total, and the circle is 122. So if we subtract those two things, we should get how far it is from the ground. Okay, and that works out to be 13 meters. Okay, so to the middle of the circle then would be 13 meters and a radius of 61, so that puts D at 74 meters. Okay, good. Now, C value. Actually, let's do B first. Okay, so, whoops. B is equal to 2 pi over P. The period of this, it has a rotation every 30 minutes. So that's 2 pi in 30 minutes, or pi every 15 minutes. I'd love to have pi every 15 minutes. Okay, and C, because this graph starts, or the Ferris wheel, or whatever, London Eye, here we go, starts at the bottom, okay, at time 30 minutes, then if we're doing a sine graph, it should normally start here on the side. So that means we have to back up a quarter of a turn. So 1/4 of 30 minutes equals 7.5 minutes. So that's going to be our horizontal shift. Okay, 7.5. Alrighty, good. So let's write out our equation. Y equals A sine B x minus C plus D equals A, we found to be 61, sine of B, which was pi over 15, times x minus 7.5, okay, plus 74. Now that's as if we use a sinusoidal function, or sine function, sorry. You could also do this with cosine, and then you wouldn't have to worry about the horizontal shift at all, because if we're starting at the bottom, then that would just be a reflection, because remember the cos graph usually starts at the top, at the maximum. If we're starting at the minimum, then you would just have to put A as a negative and not worry about a horizontal shift. So that would look like A is negative 61 cos of pi over 15 times x plus 74. And again, feel free to graph those and make sure that they look the same. And then you can check to see that at time 0, that it should be only 13 meters above the ground. Okay? How high above the ground would a passenger be after riding on the ride for 1/3 of its duration? Well, if its duration is 30 minutes, and 1/3 of that, we're looking for how high above the ground it would be at 10 minutes. Now, since you have hopefully put this into your calculator already, if not, pause the video. Sorry about that. If not, pause the video and then graph it up. And what we're going to do is figure out when x equals 10 on your graph. Don't forget to change your window settings so that you can see your graph. So I can suggest window settings of x min is 0. We'll go for 60 minutes just to give you a couple of cycles there. And you probably want to scale it at about 5-minute intervals. Okay, so that's your x scale. And your y, again, start at 0. You probably want to go to about 140 because we know it's 135 from the ground at the top, so that should fit in. And you probably want to scale it at about 10 was probably good for your scale there. Okay, great. You should find then the intersection of your graph, or sorry, you should figure out when your graph x is 10. So if you have a TI-84 family member, then you can go second trace, and then number 1 is value, and then just type in 10 and press enter. If you have an Inspire, you want to press menu, followed by graph trace, and then number 1, and then just type 10 anywhere on the screen and press enter, and it should come up with a value of a height of 104.5 meters. Okay, good. Last part. At what time would the rider be 100 meters above the ground? So same thing, you already have your graph in there, but now because we were looking for an x value, you want to type in y2 or f2 of x to be 100 meters. Okay, then you want to find out where the two graphs intersect, and I discovered that they intersected at x equals 9.6 minutes. Okay, awesome. Practice is on page 275, so please work on that, show it to your teacher, and then go on to your formative assessment for Chapter 5. That is all.